Section, we're going to look at projectile motion. And we're going to move into two dimensions. And you already did this in your lab, but we're going to neglect air resistance just to keep it simpler. And we're also going to keep it close to the Earth's surface. Why? Because that way gravity remains constant, so we don't have to think about that either. So just close to the surface of the Earth, where the gravity is going to be about negative 10 meters per second squared. So horizontally launched projectiles is what we're going to look at today. Pretty simple idea. Before we do that, take a look at this. If you roll a ball along a tabletop without friction, you give it a little push, it's going to have some velocity here. It's going to have the same velocity here. Think about this as a motion map where this represents the position of that purple ball each second, and it should just keep rolling with exactly the same speed. Now, contrast that with a ball being dropped. I should draw more velocity vector over here. If you're dropping a ball, things accelerate. And so by this point here, it has some velocity. By this point here, it has some even larger velocity. Pretend that's a straight line. And down here, an even greater velocity, which goes off the bottom of the screen. And so it covers a greater and greater distance each moment. Well, projectile motion is just a combination of those two ideas. Take a look at this. If you roll a ball off the tabletop without gravity, which would be a very strange situation, you would discover that it moves the same distance each unit time. However, if you drop a ball, it accelerates downward. So it starts out here, next second it be here, next second it gets here, because its velocity is getting larger and larger as it falls. Well, projectile motion, like you see in this third motion here, or third frame, is just a combination of the two. So after it starts out here, and after the first second, it's down to here, next second down to here, next second or time interval down to here, and next one down to here. But horizontally, it's going this far. And I'd like you to actually put these little tick marks on your notes so you can actually kind of see it, where it is moving the same distance horizontally. What does that result in? Well, here's where I want you to do a little bit of color by numbers. So at this first one here, so here it is on the tabletop. Here it is just as it exits the tabletop, and it begins falling. So by this moment here, it's here, then here, then here, then here, which corresponds to what you see over here on the tabletop, and then as it leaves the tabletop, it begins to fall down. It's the interesting thing about this one is, did the horizontal motion affect the rate at which it took to fall? The answer is no. Still took the same amount of time as if you drifted from rest. And does the fact that it's falling affect the horizontal motion? The answer is no. It keeps moving at a constant rate. So here's the big ideas. The horizontal component or part of the motion projectile is completely independent of the vertical component. So you can treat them as separately as you want. Component just means part. Gravity accelerates the vertical component of the velocity downward at 9.81 meters per second squared, or about, remember we always make it negative 10 meters per second squared. And the horizontal component of velocity is constant. It does not change because gravity only acts vertically. Their combined effect produces the variety of curved paths that projectiles follow. If you can remember anything from this unit, it's this one slide. This is probably the biggest idea. But you're like, I don't get it. Well, let's take a look at some examples. Take a look at this. If you drop a ball at the same time that a marble shot horizontally off a tabletop, notice the distance that it falls each moment. You'll notice that the ball that was shot horizontally still falls at exactly the same rate. And you might say, well, yeah, it's because it's not moving that fast. What if you shot it really, really quickly? For example, the classic thought experiment is if you shoot a gun horizontally, the same time you drop a bullet, both the shot bullet that was shot horizontally and the drop bullet should hit the ground at the same time. Well, take a look at this Mythbusters episode.
What you got there?
This is a good one. Picture two bullets, each exactly
exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on a drop bullet, and thus, they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, Jude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24 of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24 of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
So Mythbusters claim that they hit the ground at the same time. I would argue that they did not confirm this one because of the fact that the shot bullet actually took longer to hit the ground than the drop one. It would seem like it broke physics. Well, here is my issue. I would claim that the Mythbusters made a small error. A truly horizontally fired bullet would land exactly the same time as a drop bullet. What did they not account for in their gun? And some of you might have guessed it already. Take a look at this. Here's the gun just before it shot the bullet. The bullet, it's aimed horizontally, but then watch when it fires. It recoils, which means the bullet actually took off at a slight angle upward. And yeah, if you fire the gun upward, it is going to take longer for the bullet to hit the ground than if you fired it horizontally. And that, I would claim, is why they didn't end up at there exactly the same time. All right, take a quick look at this one. The idea is here that once you launch a projectile, its horizontal velocity remains constant. So in this case, the snowmobile is going at
horizontal velocities of the flare and the
stationary.
snowmobile compare in this scene.
In this case, the snowmobile is going at a constant rate this way, and the horizontal velocity of the flare is also the same, and that's why it lands at the same spot it was launched.
How do the horizontal velocities
This
of the
time,
flare
though,
and the
the
snowmobile
snowmobile is going to
compare
stop.
after the flare is launched?
The flare keeps going with the same
How do you
horizontal
justify
velocity,
your
and so it
answer?
ends up in front. And then finally, the last example,
How do the horizontal
it's
velocities
launched,
of the flare
has
and
some
the
horizontal
snowmobile
velocity,
compare
the
after the flare
snowmobile
is
speeds
launched?
up,
Justify your answer.
so in this case, it ends up behind. You get the idea. So let's take a look at examples. We know that if we drop an object, it accelerates according to gravity. Its initial velocity in this case is going to be 0. She's going to just let it go from rest. So here's my question. At 1 second, how fast is it going to be going? And by the way, we're making gravity, if you haven't seen down here, negative 10 meters per second squared. That means a falling object's going to gain 10 meters per second every second that it's falling. So how fast is it moving after 1 second? It should be going 10 meters per second downward. Now the more difficult question. How far did it fall during that 1 second? You might say, oh, duh, it's 10 meters per second. Because, at the end here, it's going 10 meters per second, and it did so for 1 second. Therefore, it should have fallen 10 meters. Well, think about it this way. What was its average velocity during that time? Well, here it started out with 0. I guess I should probably write that on here. And it only reached 10 meters per second at the end of that 1 second. So its average velocity, 10 plus 0 divided by 2, would be 5 meters per second. And if you travel on average 5 meters per second for 1 second, how far do you fall? The answer is you should fall 5 meters. And you're like, whoa, wait a second. Well, you could actually use this equation, plug in -10 for gravity, and plug in time of 1, and yeah, you would get -5 meters as well. Or you could use our first equation, initial velocity plus final velocity divided by 2 times time gives you delta x, would also work. There's probably another one as well. I could probably think of it, but I just can't think of it at the final moment here. That's supposed to be final. That looks like a 2. Divided by 2 times time, and that would also work. So let's continue on with this one. How about at 2 seconds? How fast is it moving? You should immediately tell me, oh, it's going 20 meters per second. How far did it fall at this point? Well, we can do the same trick as before. You can either do average velocity, starts out at 0, ends up at 20. Its average of 0 and 20 is 10 meters per second. If you fall on average 10 meters per second for 2 seconds, you should go 20 meters. Or you could use the formula here and just plug in time equals 2. You'll get -10 times 2 squared, 4, -40 times 1/2, and you should discover, oh, it's going to fall 20 meters. You would also get that with the average velocity. What about 3 seconds? Well, its velocity is now -30. How far did it fall? You could use any of the methods before to find this, and you'll discover it would have fallen 45 meters. Now, what about a cannon that's shot without gravity? Again, kind of unrealistic. If it's shot at 10 meters per second, how fast is it moving at 1 second? Well, it should be going 10 meters per second, and at 2 seconds, still 10 meters per second. At 3 seconds, still 10 meters per second. The idea here is that gravity is only acting in the vertical direction, not in the horizontal. Gravity doesn't make something moving horizontally speed up or slow down. And now we can actually do some math. If you remember from the previous slides, something that is moving horizontally still falls at the same rate. And so where will the cannonball be after 1 second? Well, it'd be here and here. And now I want to briefly talk about what would be the coordinates of this point. Now, I'm going to make this cannonball here 0, 0, the origin, the starting point. And now I want to know the x and y coordinates of this thing at this point. And you're like, whoa, wait a second, how am I supposed to know that? Well, horizontally, it starts out at 10 meters per second. It's still moving at 10 meters per second after the first second. So either I would suggest probably this equation. How far is it going to move? Or you can use logic. How far is it going to move over if you move for 10 meters per second for 1 second? The answer is its x-coordinate should be 10 meters. How far has it fallen? Well, we know that it fell 5 meters, so its coordinates below the origin would be 5 meters below. All right, so now what about 2 seconds? Well, in 2 seconds, it would have moved this far over horizontally, and it would have fallen that far. What's the coordinates? Well, we've moved 10 meters per second now for 2 seconds horizontally, so we'll end up with x equals 20. And how far did we fall vertically? Well, we figured out before we would have fallen 20 meters. So the y-coordinate would be 20 meters below our origin. And so that would be the coordinates there. Finally, at 3 seconds, we'll know it's going to fall that far. It would have moved horizontally this far. So what are the coordinates down here? Well, it should be 30 meters over, and we know it's going to fall 45 meters. You're like, wait a second, is projectile motion just this idea that it's just the combination of these two ideas? The answer is you betcha. The path it will take will literally be this path down here. And you're like, okay, but I need some math. I don't want to do this logically each and every time. Yeah, we can look at that a little bit closer here. All right, next slide. So in this case, let's take a look at this one, and I'm going to go kind of fast on it. Here's the position of the ball at each second, and you can see I sort of did the same thing. Vertically, it's moving further and further each second. So I should mark the starting point here. Whereas horizontally, it's actually moving at a constant rate, going back to where our earlier diagram was. So first of all, let me put the velocities in. So it's still going to be going, it's going to be going like this. The horizontal velocity stays constant. The vertical velocity, though, is increasing by 10 each time. So it's going 20 meters per second there, 20 meters per second there, 20 meters per second there. And vertically, 10 meters per second here, 20 here, 30 here, and 40 down there, which is actually going off the end. And now the coordinates. We can actually use this equation twice. Well, let me go ahead and do this. I think you would be comfortable saying, oh, actually, the numbers are wrong. I wonder if they're all wrong. This would be 20 meters over and 5 meters down. Why? Because it's been moving at 20 meters per second since it was launched. So after 1 second, it would have gone 20 meters. And it would have fallen by 5 meters. Basically, we're using this equation right here, and we're just making that there. Let's go do the other ones quick, and we'll go through it. Oh, I did do the wrong ones here. This would be 40, and that'd be 20. 20 is the same number we got for 2 seconds falling the other one. Over here, it would be 60, going 20 meters per second for 3 seconds, falling 45. And if you check this last one, it should be 80 over and 80 down. You're like, whoa, where'd the negative 80 come from? Well, it's just that equation where the initial vertical velocity would be 0. I'm going to call that v sub y. And the acceleration is just negative 10. And so if you plug that in here and plug in 4 seconds for t, 4 squared is 16, acceleration of gravity negative 10, and the initial velocity in the vertical direction, which I call v sub y, is 0. It's only going horizontally when it's first launched. And if you plug that in, you'll discover, all right, 4 squared is 16 times negative 10, negative 160 times 1/2, oh, negative 80. Yep, you would get that. All right. So you're saying, all right, well, give me some general equations. I don't know if I can actually do this yet. Well, let's take a look at this. Can we come up with a general equation for the x and y coordinates for this thing? And excuse me here for erasing everything. I should erase too much. Well, for the horizontal, the initial velocity in the horizontal direction is just v sub x. And you're saying, whoa, what's v sub x stand for? Well, v sub x here means the initial velocity in the horizontal direction. X being the horizontal. Oh my goodness, it's going to take me longer to write this than it's worth. So in this case, it would be 20. What's the acceleration in the horizontal direction? 0. Gravity's only acting in the vertical. There is no acceleration in the horizontal. So the equation simply becomes this. And 1 or 0 times anything, this whole term drops to 0. And so how do you figure out the x-coordinate at any given time? Whoops. It's simply going to be equal to this, the horizontal velocity times time. And so in this case, the horizontal velocity was 20. And so if you take that times 1, you'll get 20 times 2, where t equals 2, it's 40. 60, and then of course our 80 down here that I accidentally erased earlier. So what about the vertical? Well, in the vertical, the initial velocity in the vertical would be any y component of the velocity. For a horizontally launched one, that's just going to be 0. And what's the acceleration in the vertical direction? It's going to be -10. And so our equation simply becomes this now. And in any general case then, 1/2 times -10, gravity would be just -5. And for our horizontally launched ones, this is going to be 0. And so our y equation just becomes -5t squared. So if you plug, for example, 2 seconds into this, you'll end up with -20. If you plug 3 seconds into this equation, you'll get -45. So these two equations are sort of our key ones if you want to just think about it very simply. This gives us our x-coordinate. This gives us our y-coordinate at any given time. Should you write these down or highlight them? Yeah, it might make your homework a little bit easier. Speaking of homework, before homework, let's try this one real quick. A ball is launched horizontally at 30 meters per second. If the cliff is 125 meters tall, how long will it take to reach the ground? So, and then how far away from it? Basically, what we're trying to do is figuring out a couple of things we want to figure out. First part of it is we want to figure out what time will the y position be, and if you're thinking about this, when the y position of our coordinates is going to be -125. And in other words, when is y going to be 125 meters below where we started? Well, if we use that equation from last time, or from the other slide, y equals the initial vertical velocity, v sub y, times time, minus 5t squared, we can solve this. Because this cannonball or this ball is being thrown horizontally, there is no vertical velocity. So we just have to solve this. -125 equals 0 times time minus 5t squared. And if we solve this, it actually works out pretty nice. -125 equals -5t squared, dividing both sides by -5. Can I do that without writing it out? Would give us 25 equals t squared. Or if you take the square root of both sides, 5 is the time. It almost looks like an S. Let me make my 5 better. And so the time that it hits ground is going to be 5 seconds. We've answered the first part. And then we can actually solve what the x portion is at that time. And you might say, wait a second, how can we do that? Well, if you remember from the previous slide, x is just equal to the horizontal velocity, which I'm calling v sub x, times time. In this case, does this ball have a horizontal velocity? You betcha. It's equal to 30. That's how fast she threw it. Do we know how many seconds it's going to take to hit the ground? The answer is you betcha. It's going to take 5 seconds to hit the ground. What's the x? How far is it going to travel horizontally by the time it hits the ground? The answer is 150 meters. And so our coordinates down here, when it hits the ground, it's going to be 150 meters from the edge of the cliff when its position is -125. All right. Hopefully it's not so bad. Now let's look at some homework questions. Oh, we got a brain break before the homework. Use the clues below to break the code, then fill in the answers for the final question. Star club equals this thing. And you might say, whoa, wait a second, I don't get it. Well, this is lipstick. And so star must mean lip. And clubs must mean stick. And if you can't quite figure out what it's trying to do on this one, it's pointing at the headlight here. which means automatically you know what the dark circle and the white circle stand for. Take a moment for this one. The question is what does triangle dark circle stand for? Yeah, I'll let you get a moment here. Think about it for a brief moment. I'm going to display the answer in 3, 2, 1, go. The first one was lipstick. The second one was headlight. Stick figure was the third one. That was a hard one. Hammerhead for that one. Drumstick there, which means triangle black circle stands for figurehead, which was kind of unusual, but hopefully you figured it out. Good. All right, now the homework. A model rocket is launched at an incredibly fast speed of 125 meters per second to travel very high in the air. The rocket reaches its maximum velocity and then falls back to Earth. And by the way, here we're assuming the rocket's already run out of fuel. So it starts out with an initial velocity of 225. And what's going to happen? It's going to go up and then fall back down to the Earth. And so its motion is going to look like this. And I realize it would actually come straight down on itself, but I'm going to do this. It's going to stop and then begin to accelerate back downward again until it hits the ground. Complete this with all known information. Yeah, I guess you could also put gravity on here. Gravity is going to be accelerating it downward. And in this case, we're going to, instead of using -10, we're going to use -9.8, I guess, to be a little bit more precise. Meters per second squared. I'm going to write that on the other side just because I'm out of space. All right. At what time does the rocket reach its maximum height? Hint, what's the velocity at the peak? And so let me draw that on there real quick. How fast is it moving when it gets to the very top? Hopefully you recognize it's going to be 0. And so solving this one, we know the initial velocity is 225. The final velocity is that. We know the acceleration is gravity is -9.8. And we're trying to solve for time. The one equation that has all of those in it, and there's other ways you could solve it again, would be this one. It's probably the simplest one. Plugging in what we know, final velocity 0, initial velocity 225, acceleration -9.8 times t, you can very quickly move the -9.8 t the other side by adding it. So we end up with that. Dividing both sides by 9.8, you'll get the time is 23 seconds. So that's the time when it's going to reach the highest point. And now you're like, okay, got that. But how do we solve the rest of this? And what's the total amount of time the rocket's in the air? Now we're trying to figure out the time. That's a brief computer glitch. So how do we figure out the total amount of time the rocket's in the air? Well, we know the time reaches the top. I'm going to use this equation. What's the total displacement from when it starts until it lands at the same spot? Well, hopefully you recognize that that is going to be 0. The initial velocity is going to be 225. Gravity is going to be this. We're all talking about the vertical direction. And if you solve that, you can factor out a t. If you factor out t, either t equals 0 or this quantity is equal to 0. If you set this equal to 0, move the -4.9 t to the other side of the equation, divide both sides by 4.9, you'll discover the time is 46 seconds. And that should actually make sense. You're like, wait a second, I could have figured that out just logically. It's going to be double the time it takes to go to the top. Yep. You could have also figured out at what time its velocity was -225. There's a bunch of different ways of solving this. D, what's the maximum height? Well, there's a bunch of different ways you could solve this one as well. I'm going to use this one because we know the final velocity at the top is 0. Gravity is -9.8. Initial velocity is 225. And if you solve that, it's a little bit of work. You'll get 2,580 meters roughly. You could have also solved it with this equation here because we do know the time, the initial velocity, and the acceleration. And if you plugged in 23 seconds, you would also get this answer. You could also use average velocity times time. That would also work. Lots of different ways. Let's take a look at one more. This one's more a projectile motion problem. In this case, Phoebe throws a baseball off the top of her building, a tall building, at 30 meters per second. The height of the building is 75 meters, and that includes her height. And so the question is how long is it going to take for it to fall down this 75 meters? If you work this one out, first of all, what's it going to look like? Include a trajectory path. The ball is going to do something like this. It's going to be traveling, and as it goes down, it forms a beautiful parabola, sort of like this, and going to land on the ground somewhere over here. How long does it take for the baseball to hit the ground? Now, here's where we're going to go back into some of our basic equations, and I'm going to write both of them here so you can sort of see it. Those two equations are very useful to get the x and y coordinates at any given time. You can also use your old equations, which is what I'm going to do down here, but I do want to list these for you. The y position at any given time is equal to v sub y times time minus 5t squared. And you might say, well, wait a second. Well, what do we know about this situation? Well, in this case, remember we always make this position the origin. And then what do we know about the position where it hits the ball? You might say, well, we don't know anything. We don't know anything about this. Well, we actually do know one thing. Its y position at this point is going to be negative 75 meters below where it started, and we have to figure out what time it's going to hit. And so one way of solving this would be to use this y equation, where this initial vertical velocity in this case is going to be 0 because it was only launched horizontally. And you could solve it that way. You could also just go back to our basics. We could just do our regular kinematics equation, just think about it in the y direction. We want to figure out when its displacement's negative 75 and it has no initial vertical velocity. The fact it's moving horizontally doesn't affect the rate at which it falls. That's that whole independence idea. Solving this, we divide both sides by negative 4.9 and then take the square root. You'll discover the time it hits the ground is going to be 3.91 seconds. How far away from the cliff will it land? Well, you can actually use logic on this one. Well, the horizontal velocity is 30. Time, we could use that. Or we can use the equation again. We know the time. In this case, we know the acceleration in the horizontal direction is 0. So we could use that same equation, but this time we plug in acceleration of 0 here. Our time is 3.91 squared. This whole term simply goes to 0, so we can ignore that. So 30 times 3.91, it's going to land 117 meters away. Hopefully this gets you started. You can use any of the 4 equations we've used before, or you can use these 2 equations to figure out x and y. You need to know time, but if you can figure out anything about what happens when it hits the ground over here, you can solve for time, and then you can figure out the other portions. Good luck. I think you should be able to do this. We're just doing horizontally launched projectiles right now. Good luck. We'll see you soon.